they're not confirmed, but I'll mostly refer to them as candidates. But besides that, mostly from the ground, we found recently we passed the number of 1,000 planets. And so I'm going to talk, my research project comes partly because there's so many planets. While 1,000 is not a very important number in and of itself, it makes a big difference to have 1,000 rather than 100 planets. And my research project is planets disappearing into stars. And this is sort of, well, it doesn't have much of a light. I guess I will have to point. One of the first major planet to be found, 51 Peg, was found with a 3-day orbit. And that was one of the big surprises of planets in the very beginning, is that these planets in other solar systems, that some of the planets are very close to the star. And they were the easiest ones to be found. But as people started finding planets that have 2-day orbits, 1-day orbits, they wondered about these planets. How could they be in such short orbits? Because if you calculate the tides that are raised by the planet on the star, you calculate that these planets should be taking, the tides should be taking so much energy out of the planet's orbit that they should be falling in. And so my research is about planets disappearing into stars, but I want to go back a little bit in my history of my history of doing planet research, and say that I'm using this research as an objective to use public speaking to accomplish major career goal, hoping for some way of going to the American Astronomical Society meeting in Washington, D.C., the AAS here. I'm not getting any light out. And then I've been relying on my savings, but I'm hoping for some support. Just like I've heard of $1 million prizes. I've attended talks by $1 million prize winners for people who've already done great, wonderful research. I think I'm close to finishing research. I've been told that my work is very good, and I just need to do all the statistics, do all the writing. And so I'm searching for a way, besides teaching English in Hong Kong, of lasting a few more months. And so I'm wanting to produce a product of speaking and writing to raise, as a means of participating in exoplanet science. And perhaps for something that I could do in the coming year, to repeat my 2009 nation speaking tour, is what I called when I had a very early version of this project. And I actually drove from Los Angeles to Massachusetts and all the way back, giving some talks and presentations along the way.
How did you happen to pick Salt Lake?
I grew up in Utah. I'm a native Utah, graduated from Woods Cross High School and from Bountiful.
Yeah. My memory is 30 feet or 30 seconds.
Well, no, I didn't say that. I appreciate that. That was a good question. I think a small group. Feel free to ask important questions, because as I practice my talk, I'll improve on the presentation. Just a few things that I've been told when I practice this in Toastmasters, a few points that people want to brought up in the very front that need some explanation before I just dive into the details. I talk about space-based planet-finding missions and ground-based planet-finding missions. And the space-based planet-finding mission that has found the most planets is NASA's Kepler mission. The European Corot mission has found a few. The ground-based planet searches, they've had longer to find planets. They've been finding them since mostly 1995, excluding some very interesting, very strange planets found before 1995. So forgive us for saying that 1995, the first planet, well, we've been finding planets since 1995, other than the 1992 found some pulsar planets. So my history earlier on, with really working on a planets project, I did do some astronomy here at the University of Utah. That's another reason I'm here, and at Georgia State. But I had the chance to be the first staff astronomer at a private observatory, a global telescope observatory. And here I am in Hawaii helping with, we actually did mechanical, putting together work of the telescope, refurbishing it, and I was the lone astronomer on the mountain when we actually had some fires come up the mountain. So we've had some dramatic times. We weren't too terribly, the fire wasn't going to burn the telescope because there's nothing to burn there, but we were pretty worried about what the smoke could do. So the Kepler mission, to start talking about actually finding planets and how did we get the statistics of 1,000 planets plus. And I should mention that the thousands of Kepler candidates, I think it's above 3,000 Kepler planet candidates. The reason we call them candidates is that there's false positive mixed in. When you have a transiting planet, it's very hard to tell the difference between a transiting planet and a diluted eclipsing binary. And by that is, if you have two stars that are in eclipsing binary, if you happen to have a third star that's somehow reducing the light, you can reduce the level of transit to what looks like a planet. So any transiting planet, in fact, most of the ground-based searches, I think that you'll hear ratios of there's like 2 to 1, 3 to 1 false positives on ground-based searches. The Kepler spacecraft, it has such precise shapes of the transit curves that they're able to tell the difference. And by a transit curve, what I mean, I should back up. A planet transit is, in our solar system, Venus will transit the sun. And the difference between a transit of Venus and an eclipse of the moon, the only difference is a matter of magnitude. The eclipse of the moon just covers the sun. And that's cheating because the moon's sort of cheating because it's so close. Venus is getting not quite what you would see if you were light years away. But still, if you're outside during a transit of Venus, you obviously can't tell the difference. It takes sensitive equipment to to detect the reduction in light. And if you want to get really sensitive measurements of stars, having big planets transit, planets bigger than Venus, then it's very difficult to do from the ground, and we've had a lot of success from the ground, but if you really want good curves, you really need to go into space.
There's a lady in Kanab that
Oh, yes.
she's got 6 or 8, I'm not sure. I can't come up with the name. Her husband's Jerry.
Is it Kathy? I think she's got like a
could
24.
Could be Kathy, but she's got 6 or 8 confirmed of her own.
I think she does confirmations more. She helps with confirmations more than she discovers them.
Well,
Because
she's got, I think she's credited with at least 6 discoveries. Something like that.
well, what would happen?
And I don't want to interrupt your talk.
Well, it's an important point that validation and confirmation.
Yeah, she's just an
versus-
individual, but they
Yes.
have a very exotic.
I've seen her name up, and it's slipping my mind. She works with Bruce Gary, I think. Bruce Gary helps with
I
they
believe
collaborate.
that's correct.
And so what you have to do with all these planet finding, the next slide actually shows she's probably helping with this one or another one. She doesn't have this. This is a planet finding optimized. These are either small telescopes or actually just big cameras. And the reason you have 8 big cameras rather than one large telescope is to cover a large area of the sky. But these produce really lousy curves. And so what they'll do is they'll take the lousy curve produced by this, and they'll tell her, Kathy, or whatever her name is, can you look at these? And she will get a much better transit curve. And so that's step one in the confirmation. Now, I doubt that she's got spectroscopy to do a radial velocity measurement.
I can't tell you. It would not surprise me if she does.
Those are usually the big professional to have an actual spectrograph. Her niche really is to do that mid-level transit verification, that it's a good transit. But for the ground-based curves, you just can't get a good enough curve to be absolutely sure unless you do this other method of you look for the wobble, you look for the radial velocity wobble, spectroscopic. The basically it goes from red to blue, and you want to match that up with the transit curve. So I'm quite sure that she does the good characterization, because that's actually what I was doing. I wasn't the initial discoverer, the initial one to find it, and I didn't do the final validation. So now that we have like 1,000 planets, we've found some issues that the planets, for example, have many eccentric orbits, and there's many planets that are close together. And so I've made the analogy that planets are like bumper cars. That if you have a planet in an eccentric orbit, then what happened to the other planets that were in the circular orbits? And I'm making the point, other people actually said that planets are like bumper cars, that they're moving each other around. I pointed out what's happened to the planets that may not be there still. And so if you take a distribution of the planets, and this is a fit of the Kepler planet candidates, it turns out that for the giant, medium, and also the small, not shown planet distribution, the data fit, which I have here in dark, is that beyond a little bit more than one day, the number of planets in logarithmic space just goes up fairly smoothly, but there's a drop-off, and this drop-off is expected due to tides. And so what I've done, I've taken a dashed line of initial occurrence, and then what these dotted lines are for different strengths of the tidal dissipation. And the way that physicists do the tidal dissipation, the higher number, 10 to the 8th, is actually the weakest dissipation. It just comes out of the physics. So this is, if you calculate what an initial distribution is, the planets over here will have gone into the star even under the weakest tidal dissipation, and then for stronger and stronger, they go further in. And the giant planets raise more tides on the star. The amount of tidal energy dissipated is proportional to the mass of a planet. Mm-hmm. So you would expect that there would be fewer planets here, that this decay would be greater here than here. It's not. It's the opposite. There's more giant planets. Now, a lot of people, when they were looking at this first, and I don't think people have really looked at what happens going from giant to medium planets very well, because a lot of people said that in order for there to be planets of only 1 day period, that the tidal dissipation has to be really weak. Otherwise, for example, there's a planet of 0.8 days, and what they say about this WASP-18 planet is that did we really catch WASP-18 at a very lucky time right before it falls in? It's just statistically improbable that if it's only going to be above in that orbit for a few 100 million years, it's just not very likely that we're going to catch it. And so they say in order for it to be there for several billion years, it's got to, the tides on the star have to be weaker for planets than they are for binary stars, because the tidal dissipation strength is pretty well known for binary stars. There's a lot of binary stars. And they say, well, it's the tidal dissipation strength there's some other factor that we don't understand. And I'm saying I don't think so. Because this is, for medium planets, this is really about what we would expect. I think we did catch some of these planets at this supposedly special time, but it's not a special time. The answer is that planets just are regularly going in other solar systems. And that there's a higher flow of giant planets than medium planets. And I also point out, though the statistics aren't very good, probably a little bit lucky, but it was done by somebody else, that this power index here, the slope in log space, is really close to what you'd expect from tidal infall. So giant and medium, but not small planets, are really falling in. They're, maybe you shouldn't use the word fall, some people get upset. But so I said, well, what if you just calculate with different tidal dissipation strengths what would happen if the currently known population of planets, if it goes in, and what the other people are saying, that are trying to use a weak tidal dissipation strength, they're saying that you don't want tidal dissipation to be very strong. And so, I guess the labels came off of this. This is the weakest tidal dissipation. I mean, this is, the weakest tidal dissipation, but for strong tidal dissipation, this population up here, you need to supply the planets from these coming in here. And so what this is saying, what other people are pointing out, that to have planets here, it's a special time. Unless you can just simply fill this up. And I'm saying, yes, you can fill this up. And if you fill this up with just a new supply of giant planets, you don't need, you need on the order of 10 to the minus 13th or 10 to the minus 12th planets per star per year. So that's one saying that every gigayear that there's one planet coming in for every 1,000 stars. That's actually reasonable. There's, if many planets have stars, and if solar systems or planetary systems, if they're regularly destabilizing on occasion, then there's really nothing unreasonable about that. So I think that there will be a debate of these two hypotheses. And then furthermore, I've found that as you have higher orbital eccentricity, that the iron in the stars is actually correlated. And people didn't expect to see this. Astronomers have thought for a long time that, it could be either Latham or Stefan et al. It's both of them. People have thought that the more iron you have in stars, then the more likely you are to form planets. And that's why there's a known iron planet correlation for giant planets. But we're actually finding, it's a little bit of a surprise, that for small planets, that correlation seems to disappear. In fact, our sun does not have an especially high concentration of planets. And people are trying to say, well, maybe the terrestrial planets, maybe they stole the iron. Maybe all the planet material is locked up in the planets. Well, the other hypothesis, the one that I'm favoring, is the planets, in fact, do go into stars. But when you have all these eccentric planets, that you're actually polluting the star with, and when we say pollute the star with iron, we say that because stars have just pure hydrogen and helium. Now it turns out that this pollution hypothesis has been around largely in the form of polluting the star with material from the disk. And so I'm making a little bit of a separation between, we actually have three reasons for having correlations between the amount of iron in the star. There's formation, but pollution, you have two possible modes of pollution. You have pollution from the disk, but I'm promoting that these planets could have caused actual infall of whole planets.
Would it have importance in what part of the star's history that you're
that's-
talking about? For instance, when our sun is progressing towards a red giant, and the rocky planets are going to be melted, the sun will then have quite a bit more iron than it does now. And would that be feasible with some of the stars that you're looking at that are heavy iron? Are they a red giant or just a standard star?
I'm trying to exclude all the old stars, all the evolved stars, because that is another subject.
That would weigh by excluding them, you get rid of that problem.
Yeah, so I'm just to separate out very close research subjects. There are a few good papers on the effects of red giants eating or consuming, coming out rather than the planet going in.
Correct.
And I should put in an important detail about stars, that stars like our sun have a convection zone that it's believed that could trap this sort of material. The radiative zone in the center wouldn't let iron in. And that's very important because a lot of astronomers, their initial reaction is no way. A star is far too big to be polluted. It is far too big. You can only pollute the convective zone. But you may run into that sort of trouble with a red giant. And I should calculate that again. And that I'm not sure that once a star really spreads out, I think that you might not be able to see an Earth mass of iron.
Well, some of my questions, I'm very much a lay person.
That was a very good question. It really was. Because I'm glossing over, and I found that when you give talks, if you're going to get to your point, you can't look at all your questions. You can't look at every possible question for the audience. But for you to be understanding what I'm saying and for this to be a productive exercise, it's good to connect up to those sort of things. Another thing that the people look at in the case of evolved stars is there's some claims of some possible correlations with the rotation, that the planets may speed up stars. And so that's something.
So speed up the star.
The star's rotation, yes.
And so would that decrease the tidal forces then?
Yes, it would.
It would have.
I suppose if the rotation of the star is near the orbit of the planet, then there'd be lower tidal, the lower energy loss of the tides, right?
Exactly, yes. Yes, there is a tau boo. The star is in synchronization with the planet's orbit. And so, and you actually said exactly the right thing. You would almost say that there would be no tides, but stars lose angular momentum to their stellar wind, magnetic field, which means that the star still, since the star will be slowing down, then it would put a slow tide onto the planet, because the star would lag a little bit, and it's also very interesting about stars going in. There's a grandson of Charles Darwin was an astronomer, not a biologist, and he, a few years ago when I started looking at this myself, I rediscovered the Darwin instability. It turns out that planets above a certain, most planets that we know now are capable of, they will fall in. But if you have too massive of a planet, you can bring a star into synchronization. And when you bring But if you bring a star into synchronization, there's a point when a planet's too close. There's nothing stopping the planet going in. It just doesn't have enough angular momentum, and that's called the Darwin instability. And so these two planets, when a planet is synchronized with the star, once it gets within a certain distance, it'll just fall in. It won't have enough angular momentum to keep the star in sync. And it's just speeding up too fast. And then it'll very rapidly go in. So Tau Boo may be as doomed as the rest of the other planets. Just a little bit of a delay. So I found a difference if you separate out the iron-rich and the iron-poor systems, that there's a lot more, and if you plot them by orbital period, you'll find that the iron-rich systems, below 500 days, they have a much higher eccentricity. And so this is something that a woman and a graduate student at Harvard also found at about the same time I did. And I published it in conference proceedings in 2012. She got the refereed paper this year. So both of us each did. I was a little bit more first. Both of us did quite well first, and I hate to trumpet being first, but if you want to, when you're in the job market, you have to do that.
You have to.
One thing I found here, though, is that between 500 and 600 days, there is just this funny peak. And it actually, if you extend the range just a little bit out of between 500 and 600 days, you actually widen the peak just a little bit. So I'm doing some Monte Carlo analysis, that is some statistical models to guess to see how likely this is, but I think that this has to be a real feature. And I think that this could have to do with that maybe planets from further out, that if they're beyond 600 days, that maybe they don't scatter. Maybe there's nothing to scatter in that 500 to 600 period range. And if you wonder why would there be such a distinct difference between 400, 500, 600 days, well, it turns out that there's what's called the snow line in planet formation. The planet formation probably, actually planet formation of giant planets probably mostly happens far away enough for ice to freeze. And we call that the frost line or the snow line. So that could happen. And I should mention the other woman, she's made a very good hypothesis of how the formation mechanism could account for having eccentricity and iron correlated. She said that if you have more iron, and if that forms more planets, that they would likely scatter each other more if you have more crowded planets. And so she's still taking things from a formation reason. I really think that this is one case, though, where the two explanations could be very complementary. Now, I've also found that when you have a stellar companion, that this correlation goes away. And I think, I would say in that case, that's probably due to formation. And what I mean by the correlation goes away, if you have a stellar companion, planet systems with a stellar companion, regardless of the eccentricity, and pretty much regardless of the period, have high iron. And so I think the explanation there is, in order to form planets in the presence of a binary star, you have to have more iron.
I have a question. We talk about stars swallowing their planets. If in your bumper car scenario, has anybody calculated how many planets would be ejected from the system? What percentage would be ejected versus consumed by the sun?
Well, that's why I'm saying that with these numbers, and if I'm able to find the rates of planets going in, we don't, before I presented these rates here, I really haven't seen the theorists produce that many numbers and ratios. They say that that there will be planets ejected, exactly like you say, ejected from the system, ejected from away from the star, that there'll be collisions, that there'll be direct collisions with the star, there'll be eccentric, some of the planets will be left eccentric after scattering. Now, all these things can happen with scattering, but they're a little hesitant to put the numbers on it. And we've seen a lot of eccentric planets, but we really, before, I think in some ways, and maybe I'm over promoting myself in the job search, but I think in some ways this is the first number, and I've almost got a number, but to read my number off, you have to know what the strength of the tidal migration is. That's got cut off there as a cube. So I think that is an important question: how many of the planets would get ejected? I've talked to some of the theorists, and they say that, oh, there's more or less. They seem to have an idea of the numbers, but they don't want to publish them. But with scattering, that definitely can happen.
They probably don't want to publish them because they really don't have sufficient data to back up their thoughts.
And you always joke.
If you have the data, usually you'll publish it.
I would think that simple orbital mechanics, you could get some software and throw a bunch of Monte Carlo planets in and just measure the percentage consumed. I'm surprised nobody's done that. Maybe,
well, they have.
Maybe it's more complicated.
I think what it is that they find if they tweak their models just a little bit, that one number goes up and the other number goes down so much that when you have a theoretical model, you become really hesitant to make a too definite a prediction if you notice that the outcome is too sensitive to initial conditions.
That makes sense.
Okay, so also I found here, this is something that was earliest found in 2002. I probably should put some arrows down here. That when the mass of the star rises, the mass of the convective zone actually decreases. So that's a little confusing, but so as you're going up here in mass of the star, you're actually going down in the mass of the convective zone. And it was found in 2002 that the amount of iron the amount of iron in a star actually goes up in a manner that the authors in 2002 thought that it did indicate that there had to be some pollution happening, either from the disk or whole planets. And I'm finding that the population of eccentric planet does follow this same pattern as well, but just up higher, as you'd expect for pollution. The authors in 2002, there weren't enough planets for them to look at eccentricity, so there was no way that they could find it. But I'm really grateful to Mayer and Chavoyer, or their names, for really doing a wonderful paper in 2002. So I'm going to do public presentations. The one thing I forgot, I do stand-up comedy, and I hold a buttersquash and I hold a pomegranate and say hot balls of gas. And I realize I left those home, but it's the buttersquash and pomegranate are great because you actually have good colors for star. You have an orange star that's a little bit larger, and you have a red star that's a little bit smaller. And so just making a point of saying I'm participating, working on doing, on launching, I'm relaunching my blog tomorrow. One thing I'm having to think, if I'm seeking philanthropists, and it's really a big process to figure out how to do this. But I will be, I'm looking at Kickstarter and Rocket Hub and some of the crowdfunding websites. And there's pros and cons that I decided I really need to do this talk first before deciding those, and just simply making my blog as my primary go-to source. So, and I'm wanting to use the recording of this talk to show that I'm not only doing something valuable, but if I haven't been able, because I'm working alone, and so getting papers through peer review is always a big challenge. And I'm willing to put my work out in public, hoping to get some support and hoping to get through this tough job market with all the difficulties for federal budget things. So I appreciate everybody coming, and thanks for your questions on that. That really, I think we did have some good communication, and that's the point of giving a talk.
Thanks for your coming. It's when you're doing I know what it is to do your own funding.
You've done it.
Yes, sir. I started my own business 22 years ago. I still work.
Do you have any questions, Carlton?
Well, I was wondering how you take into account the probability, you have some distribution of planets, how you take into account the probability of discovering it, because it's based on the data. And the data, of course, has got some kind of selection criterion, because certain orbital characteristics wouldn't lead to discovery and others do. So there's a kind of a selection process based on what you can see and what you can't see. So can you take that into account in your analysis?
That is,
As we call that acceptance in the trade.
yeah, it's whether, could some of this come from selection effects? Yeah, I've looked at this, and I'll have to change this. There's some selection effects. I don't think that for the transiting planets, you have to weight all of the planets by the probability of selection. I've worried, for example, would there be any greater or lesser likelihood of finding eccentric planets, for example? Because when an eccentric planet, if you're looking for it with the radial velocity method, rather than, it's hard to remember. Instead of getting a sine curve, you get a curve like that. So I was wondering if that could affect the if that could affect the detection probability. And so I think that the transiting planets are a little better. That you worry with and the Kepler planets are a little better, because with the radial velocity planets, people have chosen planets that have higher metallicity, and so there is an obvious bias from the get-go with those. But that's what I think is good about the radial velocity, is that other than the small possibility of, would a signal like this, would it be a little easier, a little harder to see? I don't, especially with metallicity, I think that that's pretty hard to have happen, but you have to address that possibility. But certainly the radial velocity planets, the stars, the metallicity of the stars is higher than for the transiting planets, because the transiting planets, you're just looking at a whole field. You don't pre-select by metallicity. And so you're hoping that these patterns that come out, you're hoping that I'm hoping that these planets, that these patterns that come out, that they hold across different techniques. And that's one thing I've found, is that if you separate out the radial velocity planets and the transiting planets, that the correlation that exists, you have more iron with more massive planets because you have a less massive convective zone. I've reproduced that with both the transiting planets and the radial velocity planets, but I found that you have to separate out the two because you can get a bit of a false signal if you mix them in, because the transiting planets have lower metallicity and the radial velocity planets have higher metallicity. So the real population is represented by the transiting planet sample. You know for the radial velocity planet sample that these were pre-selected. The problem with the ground-based transiting planet sample is you've only got planets of periods up to about 5 days. There's not really very many from the ground. There's not very many planets that have been found with periods longer than 5 days. No, the Kepler spacecraft found them out further out. And so I think we have to put in the caveat that anything with using these ground-based search statistics really needs to be reproduced with the Kepler candidates.
Is that because of distortion from the ground-based observatories have quite a bit more distortion than does Kepler?
Well, it's better to do statistics.
Tracking.
It's better to do statistics with stars that you haven't selected out in advance for having more metallicity. Because the radial velocity searches, they more or less, they select a group of stars. And once people started finding out, discovering that there was this planet metallicity correlation, when they said, well, we want to find more planets, so they specifically chose stars.
Okay.
But I don't think that they were able to tell that whether these planets would be eccentric or not.
By the way, that lady's last name is Foote. F-O-O-T-E.
Oh, Cindy Foote, yes.
Cindy Foote.
Cindy Foote.
I've been to their observatory.
Have you?
Yeah.
Yeah, that really jumped out at me when I was in Taiwan, working in Taiwan, when I was looking at the extrasolar planets database that run, it's like ETZ, I think it's Hungarian or something for, and they run a database of all these planets, and it's like Cindy Foote from Utah has a 24-inch telescope. Of course, there's someone connected with SLAS that has like a 1.8 meter telescope here in Utah.
Yeah, 1 meter mic.
I haven't heard that he uses this for.
Well, it hasn't been really used for any purpose yet. It's parked in, there's a fellow by the name of Steve Dobbs, I believe, that owns a company that does mirrors, and it's parked in a gated community over in Sherman. I've actually looked through it, and I was amazed because I'm on a step ladder 4 steps up, and I don't like ladders at my age, but that telescope was so finely balanced that I could track. It's like a dog. It doesn't have tracking on it yet. He'll put tracking on it, but it's hand driven, and I could pull it, and I'm not necessarily very strong anymore. And amazing piece of engineering. He had no plans. Everything was in his head. He's a long-haul refrigerated truck driver, and he designed it in his mind while he I don't know how or where he bought the mirror. The mirror alone weighs 900 pounds.
I wouldn't recommend doing it without plans.
I wouldn't brag about it if I did.
I've learned the importance of writing, but also I think that being able to publicly speak just show that you have the willing to do it.
Our club goes down to Bryce every June in the dark of the moon. Bryce puts on an astronomy festival, and we, SLOS, co-host it, and we will take 40 to 50 telescopes down. And he plans to have it there this year. It takes almost a semi to transport it. But it breaks down into, I think, three segments, but it's 34 feet long.
I had the opportunity once to look through the 100-inch at Mount Wilson, and I was just shocked at how three-dimensional it. I looked at a cluster and looked at a galaxy, and I don't understand why, even though I got my degree in physics, I can't understand why the view is so much better, because I always hear that with bigger telescopes, the atmosphere just blurs the image, and you don't really get, you get more light, but you don't get more of a high quality image. But when I look through it, I was like, well, you do get a better image. All that I've been told on that didn't seem to quite be right.
Well, now they're coming in with adaptive optics, and I guess you get I haven't had, our club went up to Haniakala on Maui.
Haleakala? Yeah, that's
I
right.
don't know how to pronounce it. J.D. Armstrong lives in, he's a,
Yeah, I know JD.
you know J.D.?
Is he from Utah?
He is from Utah. In fact, he was at our board meeting last night,
Oh, really?
and he's visiting his mother. And,
Wow.
and Roger Fry could probably put you in touch with him if I don't know JD's. I talked to him when my brother lives in Kona, and I wanted to go up on Mauna Kea, and I tried to get some contacts at the University of Hawaii to take. I was by myself. Our club went up as a group, but I realized that I'd have to buy oxygen and take it up, or I'd probably have some problems. But I ski at the top of Park City, and that's 11 something, but there's a lot of difference between 11 and 14.
Yeah, when I went up there, it was with a group of people at a conference, and a woman got sick up there. She was throwing up going down the mountain. So, yeah. One thing I've been told, though, that if you ever do get a good chance to go up, that when you're looking at the sky, that it's good to try using a little bit of oxygen and seeing if that often your eyes are actually oxygen starved at that altitude. And I had a friend tell me that he did that, and the sky just lit up.
Interesting.
That you actually, when you're up there at night, you don't think the sky looks all that great, and it kind of surprises you. And unfortunately, I didn't know that trick when I had the chance to go up, because your eyes can't take advantage of the improvement. You might be seeing better at 10,000 feet than at 14,000. And so it's worth it to, even if you're being tough and you're feeling okay that you don't need oxygen, just try it for a moment and see if you can see any better.
Well, I would take it as a matter of course, because I just am old enough that I don't take chances anymore. But I still ski.
Well, Carlton's question is important on this I'm looking at selection effects. Certainly the people that did the earlier paper back in 2002, Mayer and Chaboyer, they looked at quite a few selection effects for this star mass metallicity correlation that they found. They do think that it may contribute to, that they may all contribute. And so sometimes your papers, you have to put that there are caveats, that you still have to look at selection effects, but you think you see something. I guess on the converse of people being too cautious, there was a paper in 2005 by a couple of very prominent exoplanet researchers where they pretty much said that there's no eccentricity metallicity correlation. And I looked at their plot, and I do see a little bit of a correlation. The problem is that there's just not enough statistics in 2005. And I think that people pretty much accept that there was a correlation now. Well, it's still new. I guess I haven't had a lot of, I haven't had seen any criticisms of this Harvard woman or my paper on that count. I guess the one thing, while I say that they're conservative, since you don't know their names, I guess I'll be a little critical also that they actually try to say that there's no accretion on the basis of there being no correlation. And the real conservative thing that they should have really have said, it's too soon to tell. But I think that just looking at their plot, I think that saying that there was no correlation when it seems to me that there appeared to be one. I think that they actually jumped in the other direction. People tend to jump in the conservative direction as there being nothing. Well, they can, I shouldn't say they tend to go both ways, I guess. So sometimes people will tend, you think you'd be conservative saying that there's nothing there, and then you got to catch yourself that you can end up jumping the other way and being too sure that there's nothing there.
When you were here before, did you have a chance to go out to our observatory in Grantsville, or Stansbury, wherever?
I went to several of your meetings when you were talking about putting it up.
Okay. Well, we have a 8-inch refractor, a 16-inch Newtonian, and a 32-inch Del Kirkham SCT. So 32 or 34.
I don't know. I haven't been out there to the observatory.
It's a marvelous telescope, but we've had some, it was down for a lot of last year. We had a lot of mechanical